And we think that these are particles. Particles, elementary particles, just like the Higgs boson, that are floating in space. And I actually skipped a slide. So this is how it looks like. So you have a big dark matter halo, sphere of dark matter, and the galaxies in the center, which is a small part of it. So the dark matter dominates, but all these dark matter particles are here, and they're here in this room. So we have built detectors that try to look for the dark matter particle. The problem is it's very hard to detect them because exactly they don't emit light, they are weakly interacting. But these experiments are ongoing and they are improving the limits. And they think that within 5 to 10 years, they should find the dark matter particle. And then they will get the Nobel Prize. But if they don't, then we have to scratch our heads again. So what could this dark matter be? But the current thing is, it's this particle, and we're looking for it. So we're not that worried. And we'll be happy if we find it. And then if we find it, we detect it, then we can also measure its properties, and then we can we have more confidence in our models. So stay tuned for the discovery of the dark matter particle.
The question is, if the universe is expanding, why is it that some galaxies are merging? They are going farther away. Why is it that some are merging?
Right, good question. So if the universe is expanding, why are some galaxies merging as we saw it? Essentially, it's exactly like Milky Way and Andromeda. So the answer is gravity. So they're already bound together by gravity. They're close enough that gravity is strong enough to attract them to one another, and they will eventually merge. And the expansion is not fast enough to change that. So there's actually sort of a contest, right? Tug of war between expansion and gravity. In these cases, gravity wins because they're close enough. And also, it also depends on the initial trajectory, right? So that was the question before, like if Andromeda was moving in this direction, but we move this direction, maybe we'll just pass each other. But the more recent measurements, or for example, well, in science, right, we know this direction and then we have an uncertainty. It could be from here to here. But then recently they had more, better, precise measurements. So we're able to say, oh, it's from here to here. So wherever it is, it will merge. And that's why we now know that this is the scenario. Right? So it's the gravity, but also the trajectory that will decide if two galaxies will merge. But essentially, the answer to your question is gravity is stronger. Yes?
I'm just a science aficionado. I've just read, however, recently in BBC concerning the Drake's equation, the Drake equation. They're talking about the possibility of other intelligent beings in other galaxies also. Do you also, as a scientist yourself, are you also open to such possibility?
Right, yes, definitely. So the interesting thing that's happening just now, in the past maybe 2-3 years, well, it started in the 1990s, let's say, is that we've detected extrasolar planets, what we call extrasolar planets, meaning they're planets orbiting around other stars in the galaxy. And recently, with the new Kepler, it's called Kepler Space Telescope. Within space, they found thousand of them. More than so, we already have 900, I think. Now we have 1,000 more candidates, and they will follow up, and they will. So we're living in time where we have detected thousands of planets outside our solar system. And then now this question of life in other planets has become a scientific question. In the sense that before, we just, it's philosophical, we have to. Now it's a question of how many are there, in different kinds of stars, and then how many of those are habitable? How many of those can have liquid water? Because that's our idea of life. Life needs water. So it has to be not too close to the star, not too far away, just right, like the Earth. So there's this habitable zone, and then the question then is if there's life, okay? And one way that we can actually do this is to if you can observe an atmosphere. And the atmosphere of oxygen, you see oxygen, nitrogen, it's a sign of life, like here. Because the atmosphere of the Earth was formed by life. So we can now start to answer these questions. As scientists, we say agnostic, meaning we don't know yet, but we can find out. The current recent estimates show that there are so many planets. So it's typical actually. So before we don't know how typical or how rare a planet is. So now it's like every star has a planet. And also, many stars have multiple planets, like planetary systems, like ours. So there can be 2, 3, 4, 5. And then also, so essentially, the galaxy is filled with planets. Okay, we can only observe planets in the relatively close to us. But you can imagine the other galaxies also have just planets. So now it's becoming more and more. It's now the holy grail of these. They're called exoplanet hunters. They just look for planets, and they are looking for an Earth-like planet. That's their holy grail. So again, if you find an Earth-like planet with an atmosphere, they win the Nobel Prize. All Nobel Prize going around. But it's very hard because the Earth is small and the star is very bright. So you have to have the techniques to do this. And then there's the question, which is the original question of intelligent life. Okay, now that's even harder. But again, it's a question of how probable you think that if you have already life, that it will lead to intelligent life. And of course, there's this popular program, the Search for Extraterrestrial Intelligence, at the SETI. We have radio telescopes that are looking for radio signals from other stars, other planets. And the idea is, if they're like us, that we have started broadcasting radio and TV signals, like we showed them, what is that? ASAP. I mean, this is like 5 years ago, Eat Bulaga or something like that. Then they will see it, right? Like in contact. But this, actually was, funding was cut for this recently, like a year or two ago, because they didn't think it was worth the money to do. So no. So maybe they're already beaming and we're not getting it. But the problem is the problem is the way you think about this, really far distances. So in the video, I don't know if you noticed that when we were zooming out, there was this blue sphere. Do you remember this blue sphere? That blue sphere is the distance that our radio signals, TV signals have traveled since the TV radio was invented in in 1930s. So in 80 years or so, that's only 80 light years. So that's only how far we have reached, and it's very small compared to the galaxy. So maybe we've only reached tens of stars. So it's really vast. So it's, for example, very possible that there's so many intelligent life in other galaxies that we can't communicate because of the vast distances. But we can think. So this Drake equation is one way. The equation of like how probable is there planets around a star. Then how probable is there life in a planet, and how probable is there intelligent life if there's life. That's the idea, that's the Drake equation, is that you put together all these probabilities, multiply them, and that gives you a sense. But the problem is each probability is hard to pin down. But what we're doing now is we're pinning down the probability of the planets in a star. That's what we're doing. So these discoveries are making one of those terms in the Drake equation more determined. That's it. Here.
Are these observations accurate because it takes billions of years for one event to happen? The observations from these events are accurate. Because of this billions of years gap between events.
What specific event? For example.
Observation.
Okay. So I guess the question is this accurate? Because it happened billions of years ago. How can we? How well do I believe? Is it believable that we can know these things? Right? Yeah, it's amazing that we do, but we do. They're accurate because we have. Yeah, this is the fundamental thing about astronomy. Actually, is that you have to think that light takes time to travel. So light, for example, from the sun, takes 8 minutes to get to Earth. So when you are outside in the sun, that was from 8 minutes ago, right? Because that's how far the sun is. And then the stars, it takes light years. And then if you go back, galaxies, it's millions of years, it takes billions of years. So what we observe now, we're actually looking at the past. And that's how we can actually trace the evolution of galaxies and the Big Bang. Is that it took light that long to get to us. And in fact, we always see the past. So you see me, not now, but from here to your eyes is 1 nanosecond. 1 nanosecond ago. So and that fact makes astronomy possible. So we call it actually, it's like archaeology. That the archaeologists, they dig deeper and deeper to the earth, and as you go deeper and deeper layers, you go older and older times, the dinosaurs, and then they can trace the, right? And astronomy, as we go out and look farther and farther out in space, we actually look farther and farther out in time as well. So we can see the past today because it took like millions of years to get to us. That's one answer to that very profound question. Yes, one more? Oh, here, good. Young people.
Heroes first, finally.
Then at the back.
As far as gravity is concerned, what is the probability of the big crunch actually happening?
All right, good, good. So the question is, I said there's this possibility that after expansion, the universe will actually contract and then get a big crunch. That's the fate of the universe. And the answer is now we know it won't happen. So there are two things. One, there's not enough mass to for gravity to win. And then number two, surprise, there's this dark energy that even makes the universe, the expansion accelerate, speed up. So now the current fate of the universe is that it will keep expanding and expanding and speeding up and speeding up and speeding up. And then we reach the speed of light, so we are lonely. And then each one will be in their own space. Stars will die, will turn to black holes, it will be cold. So it's that kind of death. Until if you extrapolate even out, you can imagine that the expansion will be so fast, so strong, that it will rip apart space-time itself. So this is the speculation of the fate of the universe, that it's called the Big Rip. Because everything will be ripped apart and maybe just energy, turn into energy. But that's if the acceleration will continue. But it's right. The point is by fire or by ice. So our current fate of the universe, death of the universe, is by ice, not by fire from the Big Crunch. So we can start to answer even the questions of the poets.
In the recent he postulates in the end of his book that the universe could have spontaneously come into being because of gravity, and this will not violate conservation of energy. Can you subscribe to such an explanation?
Right. So the question is the creation of the universe. And Stephen Hawking has his ideas, of course. I don't. But my answer would be, this is speculative theories. And right now, we don't know. So this is the edge of knowledge. That is, for example, the Big Bang Theory, or all this that we can explain. It just starts. You start with the universe already. Then the question is, how did the universe form? What happened before the Big Bang? This is all beyond the theory. Meaning, in fact, we don't know. And there are many different scenarios, alternative scenarios. There are many speculative theories. So maybe Stephen Hawking is one. And his point there is that you can create the universe out of nothing, essentially, probably. And then there's also this idea of a cyclic universe, so that you have, it's called the ekpyrotic theory, that you have a Big Bang, Big Crunch, Big Bang, Big Crunch, but in 5-dimensional space. So the answer is, we don't know. And the challenge is, how do we discriminate between the different theories with observations? Because science is always about checking the theories with observations. So the question is, are there signatures, for example, in the early universe, in the cosmic microwave background, that can tell if there are imprints from before the Big Bang? So these are the kinds of questions that these cosmologists are trying to answer. Because if you cannot connect it to observations, It's not science. It's math. And that's the problem of string theory actually, is that it's beautiful, beautiful theory, beautiful math, mathematical framework, but there are no predictions that can be checked in the laboratory and accelerators, because you need an accelerator as big as the Earth, they say, to probe those energies. What you can do is go to the early universe where the energies are not high and look for those things. It's hard. So that's the problem of string theory, for example, and also these speculative theories. So we're just not there yet. But in the future, that's why they say that string theory came decades early. So it's like, it's too early for its time. But maybe new technologies, in the next 100 years, will let us probe even beyond, before the Big Bang. And string theory, for example, also tries to unify gravity with the other forces. That's still in the future for you guys. Here at the back again.
Does anybody have any guesses about what dark matter is?
Yes, dark matter. What are our guesses for dark matter? And as I said, the best guess that we think is the most probable answer candidate is it's a particle. It's an elementary particle that actually comes out of these. Well, there are many possibilities, but it comes out of this. I'm not an expert, but there's these supersymmetric theories, and it's the least supersymmetric particle, LSP. So it's like the most fundamental or smallest mass particle, and it has these properties. So now that's why I mentioned these experiments that are trying to detect these particles. They're big underground detectors, and one of the ideas is that these dark matter particles are around us, right? So they'll be floating in and then they could hit the molecules there. And from the very, very small change in the momentum of the molecule, they can detect this dark matter particle. But it's very, very hard. But again, they think. So what they do is that they can now say that this dark matter, that they have not found particles of this mass. And then they have to, because it's easier to see the bigger masses, right? So they are we say, improving the constraints, and they think that within 10 years they should find it, based on what the particle theorists think the mass should be. So they're already reaching that limit. And they think that they will be able to make more precise measurements over the next 10 years to do this. And also just time. So over time, the probability is more. So in 10 years, either they detect it and they announce it to the world, or they don't find it, and we have to think of other possibilities for the dark matter. There's also this crazy idea. Now it's crazy idea, but some are exploring it, is that the dark matter is not a particle, it's not even matter, is that the law of gravity again is different. Because right now, the evidence for dark matter is only from the gravity. But it's harder to explain all the different observations and evidences. But that's still alive because we haven't detected the dark matter particle directly. Once you've detected the particle directly, then these theories will die for good. We hope.